So, Kolia, do you hear us?
Yes.
Okay, very good.
Yes, I can hear you. Oh, I can also see you. It's a big room.
Hi. Do you see us
Hi.
as well?
Yes, yes,
Okay.
I can. Yes, I see you.
Excellent. So, welcome everybody to this afternoon session. This is going to be a bit special because we have two online talks by Nicolai Reshetikhin and by Alan Beijing. And just before I give the word to Kolia, let me mention that this afternoon at 6:30 we have a special activity at Matemáticas en la Residencia. It's a lecture by Yvette Kosman and Tudor Ratio about Nether. Sorry about that. So, okay, with no further delay, let me give the stage to the screen, in this case, to Kolia Reshetikhin from Stanford and Berkeley, who is going to speak about superintegrability. Thanks.
All right. Can everyone hear me? Hello? Okay, so I assume that everyone can hear me, so...
We hear you.
Okay, good. So thank you very much for the invitation. It's a pleasure to be a speaker at Poisson 2022. I wish I would be there in person, so that would be Poisson plus Poisson 2022, but next time. So, so I'm not affiliated with Stanford, but I am affiliated with YMSC, Tsinghua University, and GIMSA. And these are two very interesting places where I moved last year. So after fantastic 30 years in Berkeley. And so maybe I should start with a plan. So first I'll make an introduction to various things, including superintegrability. And then we'll focus on quantum spin Kaluza-Moser chains, their superintegrability, and sort of mathematics and mathematical physics related to this. So before I start, I just want to time myself. Do I have exactly an hour or 50 minutes or 45 minutes? I forgot.
Sorry? Do you hear us?
Okay. Well, you'll have to stop me at some point. So, so first about so small digression about where I am at the moment. You know, this is not an advertisement, but it may sound like. It's just that it's a very interesting place, and I want to share my part of my experience. So, to be honest, I knew very little about Chinese universities, and I'm learning it more and more. And before I came there, so just for everyone, so Tsinghua University, this is the Chinese analog of MIT. If you want to draw parallels between American universities and Chinese universities, Peking University, Beijing University would be an analog of Harvard. And at Tsinghua University, there is this Yao Mathematical Science Center, and that's basically a math department, the mathematics department at Tsinghua. It's some kind of symbiotic organization with the proper math department. So there is a new interesting development there. It's Qizheng College. It admits about 100, over the last couple of years, slightly less students per year. The idea is fast-track mathematically talented students, and this college is something like, I don't know, Trinity College at Cambridge. So, so this is Tsinghua University, BIMSA, it's Beijing Institute for Mathematical Sciences and Applications. It's a research facility which is hiring visiting positions now. And if you want to come there, it's the target number of positions is between 300 and 500. There are postdoc positions, graduate student positions. So it's a growing, very interesting place. I mean, if I wouldn't be convinced that it's an interesting place, I wouldn't say this. There is a similar research institute based on the, on the base of International Mathematical Forum at Sanya. Sanya is the southern city in the southern island of Hainan. It's like Chinese Hawaii. So this research institute is similar to BIMSA. If you decide to go to BIMSA, you can also go there. It's a great place kind of to be and to do research. Okay, so this is about life. And now let's go to the substance. So today I'll be talking about superintegrable systems, classical and quantum superintegrable systems. It's not a new subject. It started by physicists, mostly by, in the study of the hydrogen atom. So one of the names that comes to mind immediately is Fock. So it has some history, and maybe I shouldn't talk about history. I just want to remind geometrically what it means. So what does it mean? So we have a symplectic manifold M, and what does it mean we have a Liouville integrable system? It means that we have a fibration where the generic fiber is Lagrangian. So typically this vibration is given by level surfaces of Poisson commuting functions. That's when Bn is a region in Rn. N is the number of Poisson commuting functions. But it can be more complicated. It can be just some real non-trivial non-flat manifold Bn. So that's the Liouville integrability, and the fibers of P are Liouville tori. They're called tori because if they're compact, they must be isomorphic to tori. So superintegrability is, one can say it's a refinement of Liouville integrability, because in a Liouville integrable system, say if you have a Hamiltonian that's the pullback from a function on B on the base, its Hamiltonian flow, you know that it's constrained to the fibers of P. But you don't know exactly, say if the fiber is a torus, you don't know if it densely covers this torus or whether it's a periodic, always periodic trajectory. So there is a missing part of the information. Superintegrability, it sort of refines this notion in the sense that if you have a superintegrable system, if you take a function on the base on B, its pullback on M, this Hamiltonian generates the Hamiltonian flow that will always be constrained to a k-dimensional isotropic submanifold in M, which is a fiber of pi1. So you have more information about the trajectories in superintegrable systems and sort of more constraint that's given by integrability. So geometrically, a superintegrable system consists of two projections. P1 is the projection from the symplectic manifold M, from our phase space, to some Poisson manifold of dimension 2n minus k. So generic fibers of the first projection are k-dimensional isotropic submanifolds in M. And it also consists from the second projection, P2, and generic fibers of the second projections are unions of symplectic leaves of this Poisson manifold P. That's the structure. So typically, fibers of P1 are level surfaces of 2n minus k functions. that's generating this Poisson subalgebra, but that's so that's what appear in many examples, but it doesn't have to be this way. So these functions are called integrals of motion for the following reason. So again, typically the projection P2 is given by level surfaces of k independent functions I1, Ik, and these are Poisson commuting Hamiltonians. And the Hamiltonian of a superintegrable system, it's roughly speaking, it's a function of this k independent functions, and it Poisson commutes because of all these properties. It's Poisson commutes with j's. So j's, they are preserved in such evolution. Okay, so that's what superintegrable system is, and if you have a Hamiltonian, that's the pullback from functions on B. That's a superintegrable Hamiltonian system. So I prefer to say that superintegrability or Liouville integrability, it's a geometric feature that exists on a manifold. But specific Liouville integrable systems or specific superintegrable systems, for this you have to choose a function on the base. So another geometric way to think about superintegrable systems is the following. So I don't want to make it too precise because that would be a separate talk. But the idea is the following, that instead of a Liouville fibration, where a generic fiber is Liouville, superintegrable system is a system where a generic fiber is coisotropic. So then if you take this generic fiber that's coisotropic and you do the symplectic reduction, then you end up with a symplectic manifold, which is the result of the symplectic reduction of this pre-symplectic manifold that's coisotropic fiber of P. And then you can construct P as the disjoint union of the result of these symplectic reductions. And of course, it doesn't have to be a manifold, it can be a very singular creature, but in this setting, we require it to be manifold. So, but that's the way how you can construct these manifolds, if they are manifolds. And the projection P1 is just the following. You take a point in M, it belongs to some fiber of P, and then you take a leaf through this point, that will be a point in P, and that's the projection P1. And so it's the projection from M to P, where P is the collection of these symplectic reductions. And the projection P2 from this collection of symplectic reductions to B is just something very natural. You take, because it's defined as the disjoint union, so you just project to the component in this disjoint union. So these are two points, two geometric kind of points of view on superintegrable systems. So then there is a long story about, not a very long story, but a beautiful story about the generalization of the Liouville theorem to superintegrable systems. I'm not going to talk about this, but first, so the goal is to move to the quantum case. So, but first let's repeat these geometric constructions algebraically. So when you have a Liouville integrable system, it just means the following. You take the pullback of functions on the base P. So this will be the subalgebra of functions on our phase space. And the Liouville integrability means that it's a maximal Poisson commutative subalgebra. So that's the Liouville integrability. Superintegrability means the following, that inside the algebra of classical observables, functions on the phase space, you have a Poisson subalgebra, and functions on P, and then you have another Poisson subalgebra with the trivial Poisson structure. These are functions on B. And the algebraic property of these embeddings is the following. So you take a Poisson commutative algebra, that's the smallest one, and then the intermediate one should be the centralizer, Poisson centralizer of this subalgebra in A. So naturally, if I is a maximal Poisson commutative subalgebra, then the centralizer will coincide with the algebra itself. And so in this case, J equals I. So this is the case when J equals I. So then if you think about it, say you choose, let's say, some Poisson commutative subalgebra. What will be the typical centralizer of this Poisson commutative subalgebra in A? Let's say that this subalgebra I consists just generated by one function. So then if it's a generic function, then all you have to expect is that the function itself will generate the centralizer. And so this is the case when the centralizer will be equal to I. That's a typical case. But I is not going to be maximal. So you will have just some, generically, you just have Poisson commutative subalgebra in A. But a very special case is when the centralizer is bigger than I itself. And then in addition to this, if you require that, well, okay, the rank of this, every Poisson algebra is a commutative algebra, so it has cruel dimensional, the rank of the algebra in the algebraic case. So the ranks should be the rank of the commutative Poisson subalgebra is K. The rank of the centralizer should be 2n minus K. If the rank of our classical algebra of observable is 2n. So the superintegrability property algebraically means that the rank of the Poisson centralizer of I is maximal. So that's the property of this superintegrability. And it is maximal. Okay, so this is the classical superintegrability, and there are many examples. We will focus on one example, which is the classical n-spin Calogero-Moser system. So now let's pass to the quantization. So skipping all the beautiful story about deformation quantization and problems related to it. So, well, we know that a quantization of deformation quantization of the classical algebra of observables is an associative algebra, and well, I want to say in good cases, but it's not necessary in good cases. And easy cases, it's a torsion-free deformation of this commutative algebra in the category of associative algebras. So what is a what is the quantization of an integrable system with the base B? It's a commutative deformation of functions on B such that the result of this deformation is a maximal commutative subalgebra in A. And then you can ask all sorts of questions. If you have a specific element of I, a specific representation of quantum algebra of observables, you can ask what is the spectrum of this element in this representation. And that's what physicists usually are interested in. Or you can ask for various questions about evolution and so on. So now on quantum superintegrable part. Well, the deformation quantization of the classical algebra of observables, it's the same. It's the same notion. It's an associative family of associative algebras that quantize this Poisson algebra. Now, in this case, we have the intermediate Poisson algebra. So its quantization should be an associative subalgebra of our quantum observables. So it should be deformation quantization of functions on P. And then finally, the subalgebra I again, it's a commutative subalgebra in A, quantum integrals. It should be commutative deformation of functions on B. So, but if you don't say anything else, this is just, an algebra, a subalgebra, and a central subalgebra in, well, actually, it's in the subalgebra in J. But quantum integrability means the following, that this algebra J is the centralizer of quantum Hamiltonians in the associative algebra A. So this is the definition of quantum integrable system. So let me put it this way, of quantization of a superintegrable system. So the Poisson subalgebra I deforms into the IH, into the family of associative subalgebras and our big algebra of quantum observables. And the centralizer of these quantum integrals should be maximal possible centralizer of a commutative subalgebra. So again, algebraically, we have this maximality property here, but now it's a maximality of the centralizer in an associative algebra. And as in the case of Liouville systems, integrable systems, when we have a representation of A, the main problem is to find the spectrum of quantum Hamiltonians. And again, if there are all sorts of questions related to the dynamics, then the standard discussion, but again, spectrum is very important. And then in one more definition, so if we have a quantum superintegrable system with a representation in some space H, then this quantum integrable systems is called simple if the joint eigenspaces of quantum commuting integrals are irreducible J modules. Since these are eigensubspaces of I, they are all one dimension. I mean, they are irreducible representations of I, but now we require that they are irreducibles of the centralizer of I in A of this intermediate associative algebra. Okay. So somebody please give me a sign. When should I stop? I'm just,
yes.
I have tendency to go over.
Can you hear me?
Yes.
Yeah, you should stop at 35 past.
35?
Yeah.
Okay, so, okay, great, thank you. All right, so now, if there are no questions about the general setup, then I'll go to examples. So it's if you have questions about general setup, it's a good time to ask questions.
Any questions? So no, there are no questions, Kolia.
Okay. So then, superintegrable n-spin Kalogero-Moser chain. I think everyone knows what the Kalogero-Moser system is. It's an integrable, Liouville integrable system describing n interacting one-dimensional particles with the potential either 1 over x squared or 1 over sine x squared or some elliptic functions. So what I will describe now is kind of spin generalization of it. Well, you will see what it means. So first, what is the phase space of the system? Let's describe it now. So from now on, just for simplicity, G will be simple, compact Lie group. And the whole theory can be extended to non-compact, to complex algebraic groups, to real but not non-compact Lie groups. Being simple is important. So now consider the nth Cartesian power of G. And I want to interpret this nth Cartesian power in the following way. So we have a circle, and then we have a principal G bundle over a circle. So in this principal G bundle, we have a connection. And then if you have 2 points on a circle, you have the halonomy along this arc of this connection, which is a group element. And so I want to think about elements of G to the n as collections of halonomies along arcs of a circle where we fixed n points on this circle. So in this way, it's a space. It's not a group. But it also has a group structure. And we also, when I say halonomy is a group element, it means that I fix trivialization of the bundle at these points. If I change this trivialization, these are gauge transformations. And this gauge transformation, so another kind of way to think about G to the n is a gauge group. And this gauge action on connections is just the following. It's the twisted adjoint action of G to the n on itself. From this gauge theoretical point of view, it's a very natural action. If you don't have it, if you don't have it, you may think in the following way. So there is always right action of a group on itself. That's the right action of G to the n on itself. And then there are automorphisms of G to the n. And among these automorphisms, certainly there are permutations. So what we can do is we can combine the left action with the permutation. And if this permutation is a cyclic permutation, so that's what we will have. So this is the twisted or shifted left multiplication. But then we can combine these two, left and right, into the twisted adjoint action. And that's exactly the one that has a simple gauge interpretation when the permutation element is cyclic. Of course, you can do it for any elements of Sn. You will get something, but let's not discuss it yet here. So we have the action of G to the n on itself, and they are they all lift to the action on the cotangent bundle because the left action and the right action, they lift to Hamiltonian actions on the cotangent bundle, and these automorphisms, they are Poisson automorphisms of the cotangent bundle of G to the n. So as a result, this gauge action is a Hamiltonian action, and as a consequence of this,
sorry,
the quotient space.
Can I ask something? Yeah. What is the interpretation of this cotangent bundle in terms of the gauge theoretical picture that you described?
Okay, so this is the following. We take a torus with n punctures, and we take the modular space of flat G connections on a surface of genus 1 with n punctures. So said theoretically, it's G to the n cross G to the n. And now what we can do is we can consider the neighborhood of the identity for, if we choose some basis of cycles, that's what it's going to be. But then we can consider the neighborhood of the identity for half of these cycles. And so then it will generate to T G to the n. But because it's symplectic, its natural degeneration is T star G to the n. So it's like this, you have to pass from this picture on a circle to the picture on the surface, and then this T star G to the n symplectic manifold will be very natural.
Okay, thank you. Thank you so much.
Mm-hmm. Okay, so it's a Hamiltonian action of G to the n on this space. So there is a moment map for this gauge action. So and as a consequence, symplectic leaves can be described in the usual way as the Hamiltonian reduction of the pre-image of coadjoint orbits. So this symplectic leaves, well, they are stratified symplectic manifolds. They are typically singular. So in our case, a coadjoint orbit in G to the n, it's the collection of n coadjoint orbits in G. And in this singular symplectic manifold S, we have a regular submanifold which can be described. It's a theorem that I'm not going to prove now. So it's isomorphic to the cotangent bundle of the regular part of the Cartan times the result of the Hamiltonian reduction of this symplectic manifold with respect to the Hamiltonian H action. And then after you do the Hamiltonian reduction on the product of these orbits, the natural action of the normalizer of the Cartan on the product of these orbits becomes the natural action of the Weyl group on the result of the Hamiltonian reduction. And then the regular part of the symplectic manifold is just the W. Why did I say the W in there? But it's a quotient with respect to the action of the Weyl group. Okay, so here I put the star because there's a very interesting discussion about the structure of this space for algebraic Lie groups, about the structure, its structure as a singular, as a stratified symplectic manifold, and so on. So something that I'm skipping, but it's a very interesting part of the story. So now, so this will be the phase space for spin Calogero-Moser, for n spin Calogero-Moser systems. So these n orbits, I want to interpret them as n spins. So now let's describe the superintegrability. Remember, for the superintegrability, we have to have a projection from the symplectic manifold S, a regular part of the symplectic leaf, to an intermediate Poisson manifold, and then to the base. And these projections should have certain properties. So now I want to construct these projections. So remember, I mentioned that there are two natural actions: left action twisted by the cyclic permutation, and the right action of G to the n on the cotangent bundle. So there are corresponding moment maps, and so we have a natural mapping, Poisson mapping from the cotangent bundle to the G to the n to this Poisson manifold. And then we have a two natural projections from G to the n to G to the n to G to the n. We can take either left component or the right component. So I suggest to take the left component because taking the right component will not change the story at the end. So now let's pass to the quotient with respect to the gauge action. So in our language, it's very natural. It's like passing from the in this nonlinear language of modular spaces. It's like passing from the representation variety to the character variety. So if a quotient with respect to the Poisson action of G to the N. So we have a Poisson manifold. This is also a Poisson manifold. And this is also a Poisson manifold with trivial Poisson structure. So then we choose a symplectic cleave in the one that I just described, this one. And then consider its image with respect to these projections, P1 and P2. This gives the surjective Poisson map to P, and then P2 gives the surjective Poisson map to B, which is by definition the image of P2 with the trivial Poisson structure. It's easy to prove that there is a balance of dimensions. So it's a superintegrable system, classical superintegrable system. And the number of Hamiltonian, the dimension of the basis R times N. So the number of independent functions on the basis R times N. R is the rank of G. Algebraically, we have this embeddings of Poisson algebras. And so we have a classical superintegrable system. There is an explicit description of the intermediate Poisson manifold, but I just don't want to do it because we don't have enough time. Okay, now, if I really want to talk about classical integrable system with physicists or with mathematical physicists, I have to say something about coordinates, something about choice of Hamiltonians. So let's so on the coadjoint orbit, we have natural coordinates. Say if we choose a basis in the Cartan, then we have coordinates on the Cartan, and we have if we choose a basis in root spaces, then we have coordinate functions on every root subspace, and then together these are coordinate functions on G star, and they can be restricted to the coadjoint orbit, and that's what I mean by coordinate function in quote marks. So remember that we have the product O1 plus On. So we have n of these things, and then we take the, in physics language, the total spin. So we take the sum of them. If G is compact, mu alpha is complex conjugate to mu minus alpha, and it's not difficult to find the that one of the Hamiltonians, I want to call it, I didn't explain what I means. So one of the Hamiltonians has this form. It's like spin Calogero-Moser system. So it's p squared over 2, the momentum, and then these are the conjugate variables to the momentum, and these are the spin variables. This is one of rank times n Poisson commuting Hamiltonians. So others, they are obtained by, you take a Casimir function and you evaluate it on the jth component of G star to the n. So this is the second Casimir. So if you, and yes, you take the Casimir functions and then you restrict them to the phase space. I don't know this because my mind was in quantum case. So the usual Calogero-Moser case, it's when there is only one orbit O, the group is SUN, and this one orbit has rank 1. That was considered by Kazhdan, Kostant, and Steinberg. So in this case, this Hamiltonian that I wrote has this form, p squared plus c squared over these signs. And it's quite clear that trajectories should stay inside of the regular part of the this symplectic leaf, simply because if you fix the value of h, qi cannot be equal to qj, otherwise it will be infinite. So that's the reason why the trajectories in Kalodge-Moser system, they never go to the boundary, to the part where qi is equal to qj. But trajectories for spin Kalodge-Moser system, they may go to the boundary of the regular part, and in fact they do. So this is something that we discussed with Eva for 2 years now, but we should end this discussion with something concrete soon. So you see, in the spin Kalodge-Moser case, you have the numerator that can change, it can vanish. So the system can end up at the boundary of the regular part of the symplectic leaf, because the denominator will vanish and the numerator will vanish, and then the Hamiltonians are still will be of the same value. I mean, will be final. So this is a very interesting subject, but I'm not going to talk about this. I'll switch to the quantum case. So we have many examples now of superintegrable systems, in addition to classical superintegrable systems like the hydrogen and others that were found earlier. So now let's look again at the gauge action of G to the n on itself. So clearly it induces the Lie algebra homomorphism from G to the n to vector fields on G to the n, and as a consequence of this, we have a homomorphism from the tensor power of nth tensor power of universal enveloping algebras on G into differential operators on G, and in fact it's an injective homomorphism of associative algebras. But now we have 3 of those, 3 homomorphisms.
Sorry,
Kolya, so we can
I ask something?
Yeah.
So are you using the twisted action at the beginning of G to the n into the G to the n, or this is
yes.
just it?
Yeah. The right action is non-twisted, the left action is twisted, always.
Okay, thanks.
Mm-hmm. So we have the natural embedding of UG to the n, tensor UG to the n, into the differential operators. If you look at the structure of these embeddings, you will see that it can be restricted to this fiber tensor product over the center. So these are the details of the definition. So that's just an explanation of the definition, but I don't think we should discuss it now. What I wanted to say, what's important is that you also have natural embeddings of UG to the n, left and right embeddings into this tensor product. And I choose left. So this is clearly a quantum version of what I was doing in the classical case before. So G to the n acts on our algebra here. It acts on these subalgebras. And so as a result, we can take G an invariant part of these associative subalgebras of the algebra itself and of its associative subalgebras, since the action G to the n preserves these subalgebras. And now we have the embedding of associative algebras that, as we will see, really is related to superintegrability, quantum superintegrability. It's clear that this chain of Poisson this chain of associative subalgebras is a quantization of what we have in the classical case. So we did step number one. We quantized this algebraic setting. So in the classical case, we will have to restrict all these functions to a symplectic leaf. In the quantum case, we have to find a representation, an irreducible representation of the algebra of Gn invariant differential operators on G to the n. And then we have to restrict these subalgebras to this irreducible representation. And this would be the analog of restricting these functions to the symplectic leaf. So now the representation space. Any questions about what I did so far?
Any questions?
Yep.
No, there are no questions.
Okay. So now the representation space. So there is this general mantra of how the representation theory is related to geometry. It can be made more precise, in some cases less precise in some other cases, but the bottom line is that if you take a sequence of irreducible representations of G, if you take associative algebras of endomorphisms of these irreducible representations, these are matrix algebras, and if you choose the chain of highest weights such that this collection of highest weights is behaving like this. So each mu I has components, mu rank I. So you assume that this is 1 over h as a, as I goes to infinity, and this orbit is not so. Sorry, I is not the same. No, let's see. So we have a sequence, mu I from 1 to infinity. So components are increasing to infinity such that projectively it remains finite, and then this will be the quadroid orbit through the element H in the dual space of the Cartan Lie algebra. So this is the usual way how you can mentally connect irreducible representations and symplectic leaves. And as I said, this can be done very precisely in many contexts, but let's just not do this yet. So okay, so the algebra that will be quantizing the functions on symplectic leaf, as we will see, is the algebra of differential operators on the regular part of the Cartan tensor product with endomorphisms of the zero-weight subspace in the tensor product of irreducible representations. And now V mu I are irreducible representations of G. Remember that G is compact, I goes from 1 to n. So all these spaces are finite dimensional. And the Hilbert space of our quantum spin Cauchy-Riemann system is defined in the following way. These are L2 functions on G to the n with values in this tensor product. And then you take Gn invariant part, gauge invariant part of these functions. Gauge invariance means the following: that if you act on this function from the left using representations v mu I, that's the same as the gauge action of h on the argument of the function. And then the other requirement is that if you restrict the arguments to the Cartan in one place and then the identities in other places, so this the result of this restriction should be in the zero-weight subspace of this tensor product. Okay, so we will see this. So, but so far I'm just defining the representation space. So this is the this will be the representation space of our algebra of differential operators on G. It's clear that differential operators on G to the n, they act on this space because these are functions on G to the n, and because these are gauge invariant functions, actually G invariant, gauge invariant differential operators act on this space. So this is really a representation space for the algebra of differential operators, and for the algebra of Gn invariant differential operators. And this is actually an irreducible representation of differential operators of G invariant differential operators on G to the n. I should have put this as a special theorem, but I didn't do it, I forgot. So, so now an important procedure that is natural, it's natural to call it gauge fixing. So it's a simple exercise to see that for any G in G to the n, and we have to fix G and I from 1 to n. There exists G prime in the gauge group, which brings element G to this form. It's 1 everywhere, and then the conjugation with G prime I in the ith place. Conjugation of this monodromy when you go around the circle. So, so this property doesn't fix G prime, but it fixes all other components except for G prime I. And so as a result, we have the isomorphism between Gn modulo the gauge group, the modular space of connections on a circle, and G mod G. And for the compact case, so the irregular part of it is H regular mod W. So this also gives a different realization of the Hilbert space that I just introduced. So I'll call this different realization H with the superindex H capital. So because we fixed, see, because of this property, and because we can use the element, the conjugation with the element G prime, we can bring this monodromy to the diagonal form since G is compact. So as a result, we have this another presentation for our Hilbert space, not as functions on G to the n, but as functions on the Cartan, and not Gn invariant functions on G to the n with value in the representation, but now these are just W invariant functions from the Cartan to the zero-weight subspace in this tensor product. And again, it's very nice because in general there is no canonical action of the Weyl group on the on irreducible representations. But if you will take a zero-weight subspace of any representation, then there is a natural action of the Weyl group there. Okay, so we have two ways of thinking about the Hilbert space for our quantum system, and now quantum superintegrability.
So, Kolia, You have 5
Yes.
minutes. You have 5 minutes left.
Okay, thank you. So now we can just take the action of our big algebra on this space, and we can realize this space as H mu, and then the image of this associative algebra becomes what I was announcing before, the associative algebra of differential operators on the regular part of the Cartan with values in the zero-weight subspace. And then if we will evaluate these embeddings of the algebras that we already had, we will get the quantum superintegrable system. So it's a theorem that in this case the subalgebra J is the centralizer of this commutative subalgebra I, and so we have quantum integrable system. And my iPad was stuck. So now it's easy to compute quadratic Hamiltonians. In this realization, they can be described as follows. So these spin variables are analogs of mu. So, and after this standard conjugation with this denominator of the Weyl formula, they remember that in the classical case we had R times n Hamiltonians. So in the quantum case we have the same number of commuting Hamiltonians. So now we're talking about quadratic Hamiltonians. So there are n quadratic Hamiltonians, and they have this form. The quantum spin Calogero-Moser part plus linear differential operators in Q. And the remarkable thing, if you will take the difference HK minus HK plus 1 minus HK, you will have what is called the dynamical topological Knyzhnik-Zamolodchikov operators. And here R are Felder's dynamical R matrices. And then remember that we fixed I from this set in order to do gauge fixing. So if you choose this particular I, then there are no linear parts, and then this becomes the usual quantum spin Calogero-Moser operator. And then the eigenfunctions are well known, so these are the so-called trace functions, and this goes back to Franklin and Kirillov. So in this setting, it's very easy to see that they are really eigenfunctions with eigenvalues of the Casimir, simply because Casimirs, they act independently on these variables G. So anyway, it's a theorem. And then another important theorem is that these eigen subspaces are actually irreducible J-mu modules. So what we have is a simple superintegrable system. So I finished, but there are some concluding remarks. Should I mention them, or should I finish now?
Yeah, you still have like 2 or 3 minutes.
Okay.
Yeah.
Okay. So there is also a very interesting connection to so-called two-dimensional quantum chromodynamics that was studied by Witten in the 90s. There are 2 papers, the two-dimensional QCD and two-dimensional QCD revisited. So the difference now is that there could be Wilson lines that go away from the surface. In particular, if you will take the cylinder and this two-dimensional QCD partition function, you will have exactly the propagator of the n-spin Calogero-Moser system. So, so then there is a generalization of what I was talking about to homogeneous spaces G mod K mod K, and they are related to this sort of the so-called open-closed strings. So this all coming as joint papers with Jasper Stockman. So then there is a story about, there's an existing story about the case when G is real and K is the complex subgroup of fixed points of Cartan involution. So then there are some beautiful questions about what happens with this story when n goes to infinity. There is this observation by Matitson going back to '94, which was proved by Guillaume and Seitouni in 2000. So that the asymptotical behavior of characters of SLN as n goes to infinity, and the arguments become some kind of distributions on the interval from 0 to 1. So it becomes the e to the n squared times the Hamilton-Jacobi function for the complex Burgers equation with these boundary conditions. So an open problem is to find the similar asymptotic for the trace functions, because character is an example of a trace function when there are no insertions, when all mu's, when there is only one mu and it's trivial. So, so then natural to assume that the basis should be parameterized by Diophant-Cetan basis, and intertwiners are parameterized by Knudsen-Tau honeycombs. And this must be related to the fact that the character is the partition function for the Diner model on the hexagonal lattice. How to interpret in this way these trace functions? It's not known. Another open problem is how to generalize Matitson to other classical algebras. As far as I understand, this problem is open, and Alice Guillaume just confirmed it in Helsinki a month ago. I mean, it shouldn't be super difficult, but still I think it should be done. The relation to Chern-Simons three-dimensional TQFT, that's a beautiful story. I don't have time to talk about this. Semi-classical limit, non-compact Lie groups. So this, as I mentioned, already started. Unfortunately, there is no good version, good connection between these non-compact quantum spin Calogero Mosers and two-dimensional Yang-Mills, two-dimensional QCD, but it's very similar to the fact that Chern-Simons has the same problem. And then finally, there is really, there are, in all these examples related to modular spaces, it would be very nice to sort out the geometry of superintegrable systems. We started it with Semyon Artamonov, but then there must be some kind of beautiful geometrical and cluster geometrical descriptions of, more precise descriptions of the systems. So thank you very much for the attention. Sorry for overtime.
So thank you, Kolia, for your lecture. So are there any questions or comments for Kolia? Yep. So Alfonso Garmendia has a question.
No, it's a question online from Christian Bruman. Says that he's looking forward to your next talk. And, sorry.
Okay.
But he is looking forward for your next talk.
Okay. Any? Okay. Yeah. An actual question. Yeah.
Okay. Thank you for the talk. I wanted to ask you if there is a way of making sense of a continuum limit in which this big N goes to infinity, and you might think of a loop group and the cotangent bundle of a loop group.
That's a very good question. Well, that's all I can say, unfortunately. It's very natural to look at this limit from several points of view. So with statistical mechanics, this is what they usually do. They take the limit n to infinity and see what are the thermodynamic properties of this quantum embodied system.
Any further comments or questions? So I have one question. So back to the classical spin collider Modular system. So you had this sequence from T star G to the N, and then this fire product of the Lie algebra fibering of the space of quadratic universe. So what is the geometric interpretation of this sequence? And more generally, this is related to my second question. So what is the natural occurrence of these superintegrable systems in geometry? Is there a natural setup for this?
In general, in geometry, I don't know. In geometry of modular spaces, so we have a paper with Semyon Artamonov.
Sorry, we cannot see what he's.
Okay, can you see what am I doing?
Now, yes, that's fine.
So, so this paper is about the following. It's a construction of superintegrable systems on the modular space of G-flat connections over any surface, with possibly with as many as you want boundary components. And roughly speaking, such system is determined by a choice of cycles, say C1, C2. So these two cycles, they define the system. The invariant functions on holonomies along these two cycles. These are Poisson commuting Hamiltonians because these cycles don't intersect. But then the geometrical meaning of the intermediate algebra functions. So these are the functions on loops which do not intersect these loops. You choose any graph, in fact, that doesn't intersect these loops, and then functions, corresponding functions in the modular space. These are the conserved quantities. They Poisson commute with this. So there is an interpretation, and it's in this paper.
Okay, thank you so much. Mm-hmm. Oh yeah, there seems to be another question online.
Yeah, this is a question of Rui Fernandez. He asks if superintegrable systems that are also known as non-commutative integrable systems. A large class of these is given by multiplicity of free Hamiltonian spaces, which were classified by Knopp. Was the quantum version of this being worked out?
That's a very good question, and I should make yes. I should say that there are two other names for superintegrable systems. One is non-commutative integrable systems, because these integrals J are not Poisson commutative anymore. And the other one is so-called degenerate integrable systems. And degenerate, it's a special story. It's basically tells us that the quantum system is highly degenerate. If you take the multiplicities of eigen subspaces of this commutative algebra I, they behave as 1 over A. I mean, they behave like in geometric quantization spaces. They go to infinity as H goes to infinity. So for these multiplicity-free Hamiltonian spaces, I'm sure there is a representation, theoretical analog of this. I didn't think about it, but it's a very good question.
Yeah, there is another question in the audience. Let me go there.
Thanks for the talk. In this example of the spin system, you considered mostly the regular part of the reduced phase space of the cotangent bundle mod out by the GN action. What is known about the structure of the singular strata? Are they also superintegrable, or do you have like a concrete description of the singular strata?
I wanted to do this for several years, and I have never done this. So this.
Păi mă apucat să mă uit.
Oh. Okay. So anyway, There are two. Okay. Yes. So as I mentioned, this regular part is not complete for spin collision modular systems. There is a question of how the trajectories go to the boundary. So in this sense, yes, I expect that there should be some life on singular strata, and most likely there will. I don't know. Well, whatever I will say will be a guess. So perhaps the best way is not to say anything, except for conjecture that yes, there must be some superintegrability on singular stratas.
Okay, so any further comments or questions? So if not, let's thank Colli again. So we are a bit behind the schedule, so let's resume in 5 minutes.